Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. I sure appreciate the feedback I hear on different platforms and the episode recommendations. Keep them coming. I'm excited to try and get to as many as I possibly can. Today's episode is from a Wikipedia article titled Magnesium. Magnesium is a chemical element. It has symbol Mg and atomic number 12. It is a shiny gray metal having a low density, low melting point, and high chemical reactivity. Like the other alkaline earth metals, group 2 of the periodic table, it occurs naturally only in combination with other elements, and it almost always has an oxidation state of +2. It reacts readily with air to form a thin passivation coat of magnesium oxide that inhibits further corrosion of the metal. The free metal burns with a brilliant white light. The metal is obtained mainly by electrolysis of magnesium salts obtained from brine. It is less dense than aluminum and is used primarily as a component in strong and lightweight alloys that contain aluminum. In the cosmos, magnesium is produced in large aging stars by the sequential addition of 3 helium nuclei to a carbon nucleus. When such stars explode as supernovas, much of the magnesium is expelled into the interstellar medium, where it may recycle into new star systems. Magnesium is the 8th most abundant element in the Earth's crust and the 4th most common element in the Earth, after iron, oxygen, and silicon, making up 13% of the planet's mass and a large fraction of the planet's mantle. It is the 3rd most abundant element dissolved in seawater after sodium and chlorine. This element is the 11th most abundant element by mass in the human body and is essential to all cells and some 300 enzymes. Magnesium ions interact with polyphosphate compounds such as ATP, DNA, and RNA. Hundreds of enzymes require magnesium ions to function. Magnesium compounds are used medicinally as common laxatives and antacids, such as milk of magnesia, and to stabilize abnormal nerve excitation or blood vessel spasm in such conditions as eclampsia. Elemental magnesium is a gray-white, lightweight metal, 2/3 the density of aluminum. Magnesium has the lowest melting and the lowest boiling point of all the alkaline earth metals. Pure polycrystalline magnesium is brittle and easily fractures along shear bands. It becomes much more malleable when alloyed with small amounts of other metals, such as 1% aluminum. The malleability of polycrystalline magnesium can also be significantly improved by reducing its grain size to circa 1 micron or less. When finely powdered, magnesium reacts with water to produce hydrogen gas. However, this reaction is much less dramatic than the reactions of the alkali metals with water, because the magnesium hydroxide builds up on the surface of the magnesium metal and inhibits further reaction. The principal property of magnesium metal is its reducing power. One hint is that it tarnishes slightly when exposed to air, although unlike the heavier alkaline earth metals, an oxygen-free environment is unnecessary for storage because magnesium is protected by a thin layer of oxide that is fairly impermeable and difficult to remove. Direct reaction of magnesium with air or oxygen at ambient pressure forms only the normal oxide MgO. However, this oxide may be combined with hydrogen peroxide to form magnesium peroxide, MgO2. And at low temperature, the peroxide may be further reacted with ozone to form magnesium superoxide, MgO2 2. Magnesium reacts with water at room temperature, though it reacts much more slowly than calcium, a similar group 2 metal. When submerged in water, hydrogen bubbles form slowly on the surface of the metal. This reaction happens much more rapidly with powdered magnesium. The reaction also occurs faster with higher temperatures. Magnesium's reversible reaction with water can be harnessed to store energy and run a magnesium-based engine. Magnesium also reacts exothermically with most acids, such as hydrochloric acid, producing magnesium chloride and hydrogen gas, similar to the hydrochloric acid reaction with aluminum, zinc, and many other metals. Although it is difficult to ignite in mass or bulk, magnesium metal will ignite. Magnesium may also be used as an igniter for thermite, a mixture of aluminum and iron oxide powder that ignites only at a very high temperature. Organomagnesium compounds are widespread in organic chemistry. They are commonly found as Grignard reagents, formed by reaction of magnesium with halocanes. Examples of Grignard reagents are phenylmagnesium bromide and ethylmagnesium bromide. The Grignard reagents function as a common nucleophile, attacking the electrophilic group, such as the carbon atom, that is present within the polar bond of a carbonyl group. A prominent organomagnesium reagent beyond Grignard reagents is magnesium anthracene, which is used as a source of highly active magnesium. The related butadiene magnesium adduct serves as a source for the butadiene dianion. Complexes of dimagnesium 1 have been observed. The presence of magnesium ions can be detected by the addition of ammonium chloride, ammonium hydroxide, and monosodium phosphate to an aqueous or dilute HCl solution of the salt. The formation of a white precipitate indicates the presence of magnesium ions. Azoviolet dye can also be used, turning deep blue in the presence of an alkaline solution of magnesium salt. The color is due to the absorption of azoviolet by MgOH2. As of 2013, magnesium alloys consumption was less than 1 million tons per year, compared with 50 million tons of aluminum alloys. Their use has been historically limited by the tendency of Mg alloys to corrode, creep at high temperatures, and combust. In magnesium alloys, the presence of iron, nickel, copper, or cobalt strongly activates corrosion. In more than trace amounts, these metals precipitate as intermetallic compounds, and the precipitate locales function as active cathodic sites that reduce water, causing the loss of magnesium. Controlling the quantity of these metals improves corrosion resistance. Sufficient manganese overcomes the corrosive effects of iron. This requires precise control over composition, increasing costs. Adding a cathodic poison captures atomic hydrogen within the structure of a metal. This prevents the formation of free hydrogen gas, an essential factor of corrosive chemical processes. The addition of about 1 in 300 parts arsenic reduces the corrosion rate of magnesium in a salt solution by a factor of nearly 10. Magnesium's tendency to creep, gradually to form, at high temperatures is greatly reduced by alloying with zinc and rare earth elements. Flammability is significantly reduced by a small amount of calcium in the alloy. By using rare earth elements, it may be possible to manufacture magnesium alloys that are able to catch fire at higher temperatures compared to magnesium's liquidus, and in some cases, potentially pushing it close to magnesium's boiling point. Magnesium forms a variety of compounds important to industry and biology, including magnesium carbonate, magnesium chloride, magnesium citrate, magnesium hydroxide, milk of magnesia, magnesium oxide, magnesium sulfate, and magnesium sulfate heptahydrate, Epsom salts. As recently as 2020, magnesium hydride was under investigation as a way to store hydrogen. Magnesium is the eighth most abundant element in the Earth's crust by mass, and tied in seventh place with iron in molarity. It is found in large deposits of magnesite, dolomite, and other minerals, and in mineral waters, where magnesium ion is soluble. Although magnesium is found in more than 60 minerals, only dolomite, magnesite, brucite, carnallite, talc, and olivine are of commercial importance. The Mg2 plus cation is the second most abundant cation in seawater, which makes seawater and sea salt attractive commercial sources for Mg. To extract the magnesium, calcium hydroxide is added to the seawater to precipitate magnesium hydroxide. Magnesium hydroxide is poorly soluble in water and can be collected by filtration. It reacts with hydrochloric acid to magnesium chloride. From magnesium chloride, electrolysis produces magnesium. World production was approximately 1,100 kilotons in 2017, with the bulk being produced in China and Russia. The United States was in the 20th century the major world supplier of this metal, supplying 45% of world production even as recently as 1995. Since the Chinese mastery of the pigeon process, the U.S. market share is at 7%, with a single U.S. producer left as of 2013. U.S. Magnesium, a Renco Group company located on the shores of the Great Salt Lake. In September 2021, China took steps to reduce production of magnesium as a result of a government initiative to reduce energy availability for manufacturing industries, leading to a significant price increase. The Pigeon process and the Bolzano process are similar. In both, magnesium oxide is the precursor to magnesium metal. The magnesium oxide is produced as a solid solution with calcium oxide by calcining the mineral dolomite, which is a solid solution of calcium and magnesium carbonates. Reduction occurs at high temperatures with silicon. A ferrosilicon alloy is used rather than pure silicon, as it is more economical. The iron component has no bearing on the reaction. The calcium oxide combines with silicon as the oxygen scavenger, yielding the very stable calcium silicate. The Mg/Ca ratio of the precursors can be adjusted by the addition of MgO or CaO. The Pigeon and the Bolzano process differ in the details of the heating and the configuration of the reactor. Both generate gaseous Mg that is condensed and collected. The Pigeon process dominates the worldwide production. The Pigeon method is less technologically complex, and because of distillation vapor deposition conditions, a high purity product is easily achievable. China is almost completely reliant on the silicothermic Pigeon process. Besides the Pigeon process, the second most used process for magnesium production is electrolysis. This is a two-step process. The first step is to prepare feedstock containing magnesium chloride, and the second step is to dissociate the compound in electrolytic cells as magnesium metal and chlorine gas. The temperature at which this reaction is operated is between 680 and 750 degrees Celsius. The magnesium chloride can be obtained using the Dow process, a process that mixes seawater and dolomite in a flocculator, or by dehydration of magnesium chloride brines. The electrolytic cells are partially submerged in a molten salt electrolyte, to which the produced magnesium chloride is added in concentrations between 6 to 18%. This process does have its share of disadvantages, including production of harmful chlorine gases and the overall reaction being very energy intensive, creating environmental risks. The Pigeon process is more advantageous regarding its simplicity, shorter construction period, lower power consumption, and overall good magnesium quality compared to the electrolysis method. In the United States, magnesium was once obtained principally with the Dow process in Corpus Christi, Texas, by electrolysis of fused magnesium chloride from brine and seawater. A saline solution containing Mg2 plus ions is first treated with lime, calcium oxide, and the precipitated magnesium hydroxide is collected. The hydroxide is then converted to magnesium chloride by treatment with hydrochloric acid and heating of the product to eliminate water. The salt is then electrolyzed in the molten state. At the cathode, the Mg2 plus ion is reduced by 2 electrons to magnesium metal. At the anode, each pair of Cl negative ions is oxidized to chlorine gas, releasing 2 electrons to complete the circuit. The carbothermic route to magnesium has been recognized as a low energy, yet high productivity path to magnesium extraction. The disadvantage of this method is that slow cooling the vapor can cause the reaction to quickly revert. To prevent this from happening, the magnesium can be dissolved directly in a suitable metal solvent before reversing starts happening. Rapid quenching of the vapor can also be performed to prevent reversion. A newer process, solid oxide membrane technology, involves the electrolytic reduction of MgO. At the cathode, Mg2 plus ion is reduced by 2 electrons to magnesium metal. The electrolyte is yttria stabilized zirconia, YSZ. The anode is a liquid metal. At the YSZ liquid metal anode, O2 negative is oxidized. A layer of graphite borders the liquid metal anode, and at this interface, carbon and oxygen react to form carbon monoxide. When silver is used as the liquid metal anode, there is no reductant carbon or hydrogen needed, and only oxygen gas is evolved at the anode. It was reported in 2011 that this method provides a 40% reduction in cost per pound over the electrolytic reduction method. Rika et al. Developed a general approach for preparing highly reactive metal powders by reducing metal salts in ethereal or hydrocarbon solvents using alkali metals as reducing agents, now known as the Rika process. Rika finalized the identification of Rika metals in 1989, one of which was Rika magnesium, first produced in 1974. The name Magnesium originates from the Greek word for locations related to the tribe of the Magnetes, either a district in Thessaly called Magnesia or Magnesia ad Sipylum, now in Turkey. It is related to magnetite and manganese, which also originated from this area and required differentiation as separate substances. In 1618, a farmer at Epsom in England attempted to give his cows water from a local well. The cows refused to drink because of the water's bitter taste. But the farmer noticed that the water seemed to heal scratches and rashes. The substance obtained by evaporating the water became known as Epsom salts, and its fame spread. It was eventually recognized as hydrated magnesium sulfate. The metal itself was first isolated by Sir Humphrey Davy in England in 1808. He used electrolysis on a mixture of magnesia and mercuric oxide. Antoine Bussy prepared it in coherent form in 1831. Davy's first suggestion for a name was magnium, but the name magnesium is now used in most European languages. The main applications of magnesium are in order: aluminum alloys, die casting, alloyed with zinc, removing sulfur in the production of iron and steel, and the production of titanium in the Kroll process. Magnesium is used in lightweight materials and alloys. For example, when infused with silicon carbide nanoparticles, it has extremely high specific strength. Historically, magnesium was one of the main aerospace construction metals and was used for German military aircraft as early as World War I, and extensively for German aircraft in World War II. The Germans coined the name electron for magnesium alloy, a term which is still used today. In the commercial aerospace industry, magnesium was generally restricted to engine-related components due to fire and corrosion hazards. Magnesium alloy use in aerospace is increasing in the 21st century, driven by the importance of fuel economy. Magnesium alloys can act as replacements for aluminum and steel alloys in structural applications. Wright Aeronautical used a magnesium crankcase in the World War II era Wright R3350 duplex Cyclone aviation engine. This presented a serious problem for the earliest models of the Boeing B-29 Super Fortress heavy bomber, when an in-flight engine fire ignited the engine crankcase. The resulting combustion was as hot as 5,600 degrees Fahrenheit and could sever the wing spar from the fuselage. Mercedes-Benz used the alloy electron in the bodywork of an early model Mercedes-Benz 300 SLR. These cars competed in the 1955 World Sports Car Championship, including a win at the Mille Miglia and at Le Mans. Porsche used magnesium alloy frames in the 917053 that won Le Mans in 1971, and continues to use magnesium alloys for its engine blocks due to the weight advantage. Volkswagen Group has used magnesium in its engine components for many years. Mitsubishi Motors uses magnesium for its paddle shifters. BMW uses magnesium alloy blocks in their N52 engine, including an aluminum alloy insert for the cylinder walls and cooling jackets surrounded by a high-temperature magnesium alloy, AJ62A. The engine was used worldwide between 2005 and 2011 in various 1, 3, 5, 6, and 7 series models, as well as the Z4, X1, X3, and X5. Chevrolet used the magnesium alloy AE44 in the 2006 Corvette Z06. Both AJ62A and AE44 are recent developments in high-temperature, low-creep magnesium alloys. The general strategy for such alloys is to form intermetallic precipitates at the grain boundaries, for example, by adding mischmetal or calcium. Because of low density and good mechanical and electrical properties, magnesium is used for manufacturing of mobile phones, laptop and tablet computers, cameras, and other electronic components. It was used as a premium feature because of its light weight in some 2020 laptops. Magnesium, being readily available and relatively non-toxic, has a variety of uses. Source of light. When burning in air, magnesium produces a brilliant white light that includes strong ultraviolet wavelengths. Magnesium powder, flash powder, was used for subject illumination in the early days of photography. Later, magnesium filament was used in electrically ignited single-use photography flashbulbs. Magnesium powder is used in fireworks and marine flares, where a brilliant white light is required. It was also used for various theatrical effects, such as lightning, pistol flashes, and supernatural appearances. Chemical reagent, in the form of turnings or ribbons to prepare Grignard reagents, which are useful in organic synthesis. Other, as an additive agent in conventional propellants and the production of nodular graphite in cast iron. As a reducing agent to separate uranium and other metals from their salts. As a sacrificial galvanic anode to protect boats, underground tanks, pipelines, buried structures, and water heaters. Alloyed with zinc to produce the zinc sheet used in photo engraving plates in the printing industry dry cell battery walls, and roofing. Alloyed with aluminum magnesium alloys being used mainly for beverage cans, sports equipment such as golf clubs, fishing reels, and archery bows and arrows. Many car and aircraft manufacturers have made engine and body parts from magnesium. Magnesium batteries have been commercialized as primary batteries and are an active topic of research for rechargeable batteries.